In this video, we're going to try and prove another theorem, and this theorem is called the Squeeze Theorem. And you will see why it's called that probably by the end of the video. We're going to go ahead and write down what the theorem says. It says if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x on an open interval containing c, except possibly at c, and if the limit as x goes to c of h of x is equal to L, which is equal to the limit as x goes to c of g of x, then the limit as x goes to c of f of x is also equal to L. So what it's saying is that if on some open interval, for all the x values on that open interval, if f of x is bigger than h of x but smaller than g of x, or equal to, except possibly at c, so this is an open interval containing c, but this statement doesn't necessarily have to be true at c, and if the limit as x goes to c of h of x is equal to the limit as x goes to c of g of x, which is some value L, then the limit as x goes to c of f of x is also going to be equal to L. And this should make some kind of conceptual sense. Essentially, it's saying if I have a function that is always bigger than f, which is g of x, and I have a function that's always smaller than f, which is h of x, and f is right in between, then if the limit, and this is c right here, if the limit as x goes to c of h of x is equal to the limit as x goes to c of g of x, it's going to be the same for f of x. It's kind of because those two functions that are on top and the bottom of f of x squeeze into f of x, and they all end up meeting at that same point, or approaching that same point. They don't necessarily have to meet there. So we're going to go ahead and get into this proof. And of course, we're going to start out with what we know and using the epsilon-delta definition. So we know that the limit as x goes to c of h of x is equal to L. That means for any epsilon greater than 0, so for any epsilon greater than 0, there exists, and actually to save room, I'm going to get rid of that there exists. I'm going to just say there's a delta greater than 0 such that when 0 is greater than x minus c is greater, or is less than, 0 is less than the absolute value of x minus c, which is less than delta, then the absolute value of h of x minus L is going to be less than epsilon. And I'm going to call this delta sub 1. So for any epsilon value, there is some delta sub 1 value. I don't exactly know what it is, but I know it exists. Why? Because I've assumed that this limit exists. So now we also know that the limit as x goes to c of g of x is equal to L. So for any epsilon greater than 0, there's a delta greater than 0, and I'm going to call this delta 2 greater than 0, such that when 0 is less than the absolute value of x minus c, which is less than delta 2, then, this should be then, the absolute value of g of x minus L is less than epsilon. And there's going to be one more thing we look at based on our very first assumption, is that there is some interval that we're going to define by delta 3, so that when the absolute value of x minus c is less than delta 3 but greater than 0, when that is true, we know that f of x is going to be less than or equal to g of x, but it's going to be greater than or equal to h of x. So what is this saying? That means on some interval, because this is an assumption we make, on an open interval except at c, that this statement is true, so I'm just defining that interval to be of size delta 3. So I'm going to draw some number lines for you guys so you can see what this looks like. This part is saying that if I have x values, all the x values around C, a distance of delta 1, from C minus delta 1 to C plus delta 1, except at C, all these x values, if I'm to choose any of them, the absolute value of h of x minus L will be less than epsilon. Okay? Same here. I can choose the same epsilon. I know that the delta value exists. I don't know if they're the same delta value, but I know there's some delta value such that for any epsilon, even the same epsilon, that if I'm going to make an interval from C to C plus delta 2 and C minus delta 2, all the x values I pick in this interval, except at C, will give me back g of x values such that the absolute value of g of x minus L is less than epsilon. And here, I know there's a certain interval where this is C plus delta 3 and this is C minus delta 3, such that in this interval, when I plug in x values, except at C, when I use x values from this interval, g of x will always be bigger than or equal to f of x, which will always be bigger than or equal to h of x. So now I'm going to do something which might be a bit confusing. This is the most confusing part. I'm going to set one delta value, and I'm going to say that's equal to the minimum of delta 1, 2, and 3. So I'm picking the smallest one. I don't know what these delta values are, but I'm going to set my one delta value equal to the smallest of the 3. And why am I doing that? Well, I'm doing that because now, if I'm to define an interval of size delta, where delta is the smallest of the 3, I know whatever x value I pick, this statement will be true, this statement will be true, this statement will be true. Why? Because if it's true for all the x values in the bigger interval, well, the bigger interval contains all the intervals around C that are smaller than it. For example, if we look at this delta 3 interval, if I was to make an interval inside it, we still know that all the x values in that interval will make this statement true, except at C. So what I'm doing is I'm making a smaller interval. I'm making the interval the smallest of the 3. So I'm going to erase all this because we still have a lot to do. And we're going to say that we know for any epsilon greater than 0, there exists a delta greater than 0, where remember, delta is the minimum delta of delta 1, delta 2, and delta 3 that we just talked about, such that if the absolute value of x minus C is greater than 0 but less than delta, then I have a few statements that hold true. The first statement that I have that holds true is that the absolute value of x minus L is going to be less than epsilon. And I can actually write this as the absolute value of x minus L, or yes, is less than epsilon but greater than negative epsilon. And what I can do to this is I can add L to both sides. So I'm going to say h of x plus L, or just h of x, sorry, is going to be bigger than epsilon, negative epsilon plus L, and less than epsilon plus L. And similarly, I know that this statement will be true inside that interval. And I'm going to go ahead and write that also like this. And I know that on that interval, f of x will be less than or equal to g of x and will be greater than or equal to h of x. Now, take a look at this. I know that h of x is going to be bigger than L minus epsilon. So let me rewrite this as L minus epsilon. I know that h of x will be bigger than L minus epsilon on that interval. And I know that f of x will be bigger than or equal to h of x on that interval. That lets me know, first off, that f of x on that interval, and let me get a better marker, hopefully this one will be a bit darker, that f of x on that interval will be bigger than L minus epsilon. Because h of x is bigger than L minus epsilon, and f of x is either equal to or bigger than h of x on this interval defined by delta. And I know that g of x is going to be less than L plus epsilon. And I know that f of x is either less than or equal to g of x. So that means I know that f of x is either less than or not less than or equal to, is actually only less than epsilon plus L. Why? Because g of x is less than epsilon plus L on the interval, and f of x is less than or equal to g of x on the interval. So now we have this statement, that when we confine our x values in this interval, and remember this is going to be x values in this number line from c to c plus delta and c minus delta in that interval, except at c, that f of x will be less than epsilon plus delta or greater than L minus epsilon. And how can we write this? We can write this as the absolute value of f of x minus L will be less than epsilon. So now we have effectively shown that for any epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. And by the definition of a limit, that implies that the limit as x approaches c of f of x is equal to L, and then based on our assumptions we know that it means that this is equal to the limit as x approaches c of g of x, and also the limit as x approaches c of h of x. And that is the squeeze theorem.